Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to talk about Robot Operating System, which is also popularly known as ROS in short. So, through today's lecture, you will be able to define ROS as a middleware and explain its modular architecture. You can describe nodes, packages and the ROS computational graph, explain what is publish, subscribe, communication using topics, differentiate between topics, services and parameters, understand the sensor-computer-actuator workflow in the robotics and relate ROS concept to real world deployment on edge AI device, AI hardware, and which we are going to use in this course is the Jetson, okay, and you will be able to interpret basic robot structure and spatial relationship through URDF and TF. So, this is how my content will flow for today's class. So, first we will learn about ROS, what ROS is. We will see the history of ROS and the concept of robotic middleware, which the ROS is actually. What is the philosophy for this? Okay. Then said we are going to talk about the hardware, which is Nvidia Jetson or in Nano, which we are going to use in this course. Then building block for the ROS, various building blocks. Then the sensor, compute and actuator loop, URDF and transform, and then at the end we will be seeing how we can bridge simulation with the real deployment. So, let us see first what is a ROS, that is Robot Operating System. So, ROS is an open source framework that provides tools, libraries and conventions to simplify the task of creating complex and robust robot behavior across a wide variety of robot platforms. Okay. So, here are some of the features which the ROS has. It is a open source software, okay, and it is a middleware in the sense that it is not an operating system, something in between your operating system and the hardware, okay, and it has got a very good ecosystem having more than 1000 plus packages and 10,000 plus users worldwide, and it is a cross platform compatible. The history of ROS began with year 2007, okay, when the Stanford AI lab begins its deployment, and then in 2010 the ROS 1 was released. 2013 open source robotics foundation takes over to this. Then 2017 the ROS 2 alpha came, then further 2020 ROS Noetic came, and then 22 ROS 2 Humble, and finally in the 24 ROS 2 Jazzy. So, these are the how the ROS has progressed over time. So, why ROS 2, which is the latest version, why we are going to use that? So, there are some very good features in ROS 2, such as it is a multi-robots, it supports teams of robots coordinating without any central authority. It has feature of embedded system, okay. We can have the real time control through this one, and it is a production ready basically. It takes care of the security and it is a vendor neutral. So, the concept of robotic middleware, so as I said, so basically you have the hardware, alright, and then you have the OS layer, operating system layer is there, and you have the ROS middleware and then the final application layer, okay. So, this is how its different layers are organized, okay. So, it is a not a traditional operating system like Windows, Mac or Linux. It cannot run directly on a computer hardware. Instead, you need an operating system such as Ubuntu Linux for it to function. Okay. It is a middleware I have been talking about, a software layer that sits between your operating system and the robotic application which you are planning to have. And think of ROS as the toolkit that provide functionalities that facilitate communication system to a robot, and its main job is to make communication between different parts of a robot simple and organized. It acts as, say, as the plumbing of a robot, okay, that is provides the communication protocol so that different programs can talk to one another, okay, without the developer having to write the complex networking code from the scratch. So, that facility it gives, okay. For example, say data could be in form of, say, images, okay, if you are using a camera, then it could be in the form of the reading of the sensors, okay, say the movement command, okay. These are like, say, water, and the program are like your rooms in the building, and ROS basically provides the pipe that carry data between these rooms. So, through this analogy we can try to understand. Okay. As a developer, one can use ROS tool to send and receive data, and this abstraction is what makes ROS powerful and easy to scale. Okay. And in ROS, each function like, say, read camera or turn wheel is an independent program. Next, let us look at the philosophy. It has got modular open system architecture. The core design philosophy in ROS is basically the modularity, okay. And what does that mean? Okay, so you want to understand this, you can imagine the electrical outlets in your home, and because they use standard interfaces, say plugs, you can connect a lamp, a toaster, laptop without knowing how the power grid works, okay. So, this ROS architecture is something like this, okay. So, ROS does this for a robotic software. So, it provides modularities. You can develop, debug and test a navigation module independently, okay, say from a speech recognition module. Then you can reuse the codes, okay, because interfaces are standardized, you need not to reinvent the wheel, alright. So, you can reuse the code, okay. For example, if someone has written a world class driver for a specialized 3D camera, you can simply plug in into your ROS system. Why ROS is used for AI, okay. So, for AI driven robot, ROS is essential because it decouples perceptions from the control. So, that is one of its biggest advantage. You know, in AI robotics, we often use heavy computational model like CNN for vision, and these model process data at different speed and than the speed of the motor which we are using for the actuation purpose, okay. So, the ROS allows us asynchronous processing, okay, and standardized data, okay, it uses standardized data, okay. Next is the hardware which I have been talking about, that is the Nvidia Jetson Orin Nano. To run an intelligent middleware like ROS, a robot need a centralized brain, okay. And as I have been talking during this course, we are going to use Nvidia Jetson Orin Nano as our primary computing platform. So, what role does it has in the ROS? Okay. The Jetson acts as a centralized computing host, okay. We can use a simple microcontroller such as Arduino, okay, which have been working very well for the small robotic projects, okay, for moving the actuator, say motor, okay, but it lacks the power to run the Linux based ROS middleware or complex AI model. So, that is why we need to have something compatible with Nvidia Jetson Orin Nano. It has got edge AI capability, okay. So, it contains high performance GPU, that is graphics processing unit, and in a ROS workflow, the Jetson runs the vision node using the GPU to accelerate AI detection while simultaneously running the middleware to coordinate the robot movement. So, these edge AI capabilities this Jetson Orin Nano has. Next, we are going to discuss very important concept in the ROS, that is how a model is built, what are the building blocks of ROS, okay. So, for a robotic system to be intelligent, it must be broken down into manageable pieces that can run simultaneously on hardware. Okay. So, these are the terminologies, or what do we say, the building blocks which are used in the ROS. Say nodes. Okay. These are individual programs in ROS that perform a specific task. Okay. Then next is the topic. These are communication channels through which the nodes continuously exchange data. Then you have the services. They provide request response communication between nodes for the specific task. Then we have actions, these combine topics and services. We have messages, they define the data format used for communication between the nodes, and we have packages. They are organized collection of ROS files basically, which have nodes, messages, configuration, which are used to build application. So, let us begin with the node first. Okay. So, a node we could have, it is a, as I said, it is a single purpose programming module, okay, or a process that perform a computation. So, for example, you could have a camera node, you could have a LiDAR node, you could have a control node, you could have a SLAM node, and you could have a nav node. Okay. This type of system you can have. And in ROS based robot, you do not write one massive program, instead you write many small programs, okay, called nodes. These multiple small programs work together using ROS functionalities, and the core idea behind is divide and simplify. Okay. So, the features of node are that the single responsibility for a particular node, then you have the isolation and reliability, because each nodes run as a separate process. Okay. So, if say AI detection node crashes due to software bug, other things, say motor control mode, is not going to be affected out of it. Okay. So, that is there. And a node on the hardware. So, on Jetson or in Nano, you can utilize the multi-core CPU and powerful GPU by running different nodes on the different cores. That we can do when we talk about the implementation of it in the hardware. Okay. So, we can offload a specific vision node in the GPU, while the path planning node can run on the CPU. Okay. So, say I have a planning node in the CPU and I have the vision node in the GPU in a Jetson or in Nano. So, this way I can do that. Next, let us look at the ROS package. Okay. The package, ROS package, is basically related with the how the software are organized. So, it is nothing but it is a folder, okay, that contains everything needed for a specific functionality in the ROS. So, that is there. So, for example, you have a package say for camera, and so camera module can be there inside of this one. Then say if you have a package for detection, you could have the AI detection node inside. Similarly, if you have a motor, you could have a motor control node inside of that. Okay. So, this is how the ROS package is there, and this package contains node your source code and then configuration files as well as data file. Then next we can talk about the computational graph. Okay. So, when all your independent nodes start running and start communicating, they form what is known in the ROS as a ROS graph. Okay. This graph is peer-to-peer network of all the processes in the system, and on an abstract level for AI robotics workflow, your graph might look like something like this. So, you have a camera node. Okay, you have say AI detection node, okay, then you have the navigation node, and then finally you have the drive node. Okay. So, this could be your flow basically, workflow. Then to create a node in Python, we use RCL-Py Python library basically. Okay. Many other libraries that support ROS functionalities are available. Okay. And conceptually the workflow is always the same. So, you could have some of the features are say initialize. Okay. We tell ROS this Python script is starting up. Okay, so you could have a statement like this, then create the node. For the node creation, we could have the spin. Spin means that the node put the node into a loop so that it stays alive, okay, to listen for the data and process AI task, and then shut down. Okay. In the shutdown, it exit when the robot is turned off. So here is Python script which explains all this. So basically here you have the creation of the node, and then through main here I call these nodes. Over here I tell spin, then I tell shutdown. Okay. Now let us look at what is ROS topic basically. Okay. So as we have seen here through topics, in topic basically we have the data communication. Okay. So the most common way node exchange information in ROS is by using topics, which is based on publish subscribe paradigm. Okay. So say we could have a publisher, then and we have a subscriber. So through topic we could have the communication. Okay. So this is what the ROS topic is, and this is an asynchronous communication model, meaning nodes do not have to wait for a response to continue their work. Okay. Some of the features are the decoupling and many to many. Many to many means one topic can have multiple publishers. Then publisher and subscriber, basically what we have seen here, publisher and subscriber, that analogy we can give through the radio station analogy, where you have a transmitter which is a publisher basically, then you have a receiver which is subscriber, and the frequency is the basically topic. Okay. So this way we can have a correlation with that. Okay. So the topic is the frequency here, the publisher is the transmitter, and the subscriber is the radio receiver. Then let us look at what are the ROS messages. Okay. So nodes must speak with the same language to communicate. Alright. So in ROS this language is what we call as the message. Okay. So message types, a message is strictly defined data structure basically. It could be an integer, a string, or a complex array of pixels, and this is, so you could have the common AI messages like this. Okay. And Jetson handle high bandwidth messages, say when we are using like 4K for the video streaming. So the conceptual Python workflow for the messages, okay, could be like this. Here say when we are writing a Python node to use topics, the logic flows the same pattern as in case of the nodes which we have already seen. Okay. And the additional functionalities of topics is introduced in our custom class with a specific pattern. Okay. Say for a publisher we can have say call publisher, call publish, then for a subscriber create subscription, and so on. So here is basically basic template to create a publisher and the subscriber. So here we have the publisher, create publisher, and then create the subscriber. Next let us look at the ROS services. Okay. While topics are ideal for continuous data like sensor streaming, robots often need to perform a specific task on demand, okay, or adjust their setting without restarting their software. So a service is a communication method where one node sends a request and another node sends back a response, and this is the synchronous communication model based on the client server relationship. Okay. Now unlike radio broadcast, a service is like a phone call. Okay. So a client sends a specific request to a server, and the server processes that request and sends back the response. It has synchronicity, one to many, this feature is available. Okay. And so this is how it is. So from service client to the service server. Okay. So it sends the request and the server gives the response. Next is the action. So if you have a long running task, okay, action combines topics and services for preemptible goal oriented task with continuous feedback. This is ideal for navigation, manipulation and multi-step processes. So, for example, client sends goal to server, server accepts or rejects it, server publishes a periodic update, then you have the final response when complete, which could be result, and the client can cancel anytime. Okay. So, action uses 3 topics internally, that is goal, feedback and the results. Next is the ROS parameter. Robotic environment change constantly. Okay. So, you should not have to rewrite and recompile your Python code just to change the camera resolution or an AI model sensitivity. Okay. So, parameters allow you to configure node setting at a runtime itself. Okay. So, parameter are essentially configuration variables, say string, integer or boolean, okay, or we could have the dynamic adjustments. You can change the parameter while robot is running. Okay. When implementing logic in Python, the workflow is streamlined to focus on the interaction. Okay. So, for services we need to define service names and interface, and for parameters the Python nodes constructor say declares the parameter needed and sets their default values. So, this is the basic template for the server and the client. Okay. So, here create client, create service. So, this service server, service client and so on. So, in the service we can define name and interface, and in parameter we can declare the parameter, say for the speed as 1, like that. Next is another very important aspect here in the ROS, that is sensor, compute and actuator loop. So, you get data from the sensor, do the computation and pass on the instruction to the actuator. So, deploying ROS on Jetson hardware facilitates a continuous cycle of data flow that allows a robot to interact with the environment autonomously. Okay. So, for example, input, we have input sensing, say 3D depth camera or LiDAR data, then we have the computation. Okay, ROS node running on the Jetson subscribe to these sensor topics. Okay, and then we have the output, which is actuation. Alright. So, you have say input the 3D camera, input send this to compute, that is the your Nvidia Jetson, and then it gives to the output, which is basically the motor. Okay. You have the physical robot motion. Next important aspect is URDF and transform. Now, this robot actually, to have the visualization, this robot has to be there in the 3D environment. Okay. Alright. So, the unified robot description format, that is URDF, provides a mathematical description of the robot physical body. Okay. And its a URDF is an basically XML based file that describes the visual appearance, the physical dimension and the kinematic structure of the robot. So, this URDF comprises of links, okay, then joints. Okay. Next is the transform. This is used for tracking the robot in the 3D space. Okay. So, the transform is the mathematical relationship between the two coordinates frame in the 3D space. While URDF is a static blueprint, it will be giving you the environment, your robot and all. Transforms are the live mathematical calculations where each part is located at any time. So, we could have the transforms tree as well as asynchronous distribution. Okay. That is ROS publishes these spatial relationship to on a dedicated topic. Alright. Then how URDF generate TF basically. So, the bridge between the static URDF file and the dynamic TF system is a core ROS node called the robot state publisher. Okay. So, you have the input, which is a UDF file, this is input 1, input 2 is the joint states, and then you have the processing where you do the mathematical calculations, say forward kinematics, which we will be seeing in the next week lectures, to determine the 3D position of every link, and then we could have the output. Okay. So, it will be publishing the 3D coordinate. So basically you have the robot state publisher over here, the input is say the robot description which is a URDF blueprint, and the live motor data is basically the joint state, and the output which you will be getting will be the live 3D map. Then bridging simulation and the real deployment. One of the greatest advantage ROS framework on Jetson hardware is the ability to move from simulation to the real world deployment with minimal code changes. Okay. So, towards the end of the course, we will be seeing live demonstration of this ROS deployment, okay, in the real robot. So, we have a lecture for that. Okay. So, we have the digital twins. Developer often use gazebo to simulate the robot physical properties, say gravity, friction, and RVs to visualize. I am going to talk little more about these two, gazebo and the RVs, little later. The hardware abstractions. ROS decouples the computation logic from the hardware drives. So, that is again beautiful thing about this is. So, the bridge during development, you simply swap the simulation bridge for a hardware drive node, okay, and so that is how we can do it, right. So, you have simulation environment which is the gazebo, alright, and then you have a RV visualization, and here through simulation bridge we can switch to the hardware drive, okay, which is of course you have the real robot and say with the Jetson or in Nano. Okay. So, this can be from simulation bridge we can move on to the hardware. This RVis tool which is a visualization tool, okay. So, it is a primary visualization tool for the ROS 2, okay. It subscribes to ROS topics, renders sensor data, robot model, maps, trajectories and more in 3D. Okay. So, some of these features are the TF frames, point cloud, laser scan, images, occupancy grid, marker array, path as well as the robot model. So, these features we are going to see in the RVs 2, and in the gazebo it is a standard physics based simulator for the ROS 2 development and testing. Okay. So, basically it has got a physics engine, then sensor simulation is there, ROS gazebo bridge is there, words and models are there, ignition to gazebo is there, and hardware in loop simulation are there. So, these are the features which are available in the gazebo. Okay. So, to summarize, a robot is made of many small programs working together. ROS help these programs communicate and work as one system. Different methods such as topic, services, parameter control how this data is shared, and the Jetson allows the robot to run AI and make decision in real time. Okay. And robots follow a loop which is sense, think and act. Okay. So, you have sensor and you have thinking part, computation part and then the actuation part, and URDF and TF help the robot understand its body and position in the space. Okay. So, these are the some of the references which you can refer for your further understanding of the ROS, and with this I would like to close. Thank you.